this is our fourth and final scholarship winner reading for the summer. Our reader today is Evan O'Shea, who tied for second place in this year's HGP scholarship contest. Evan just graduated first in her class from Beaverton's International School. This fall, she will attend Georgetown University to study comparative literature with an emphasis on post-colonialist Latin American literature and intersectionality. She plans to get involved with the Spanish-speaking and LGBTQ+ communities and explore opportunities for activism in these areas. Evan's interest in Spanish started early with the Spanish immersion program from kindergarten through 5th grade. Her awareness of comparative literature, especially magic realism, evolved through summer programs at University of Oregon, St. Andrews University in Scotland, and Wellesley College. She's also a keen athlete, participating on her school's teams in swimming, water polo, skiing, cross-country, and track. Let's give her a warm welcome as she reads this summer's fourth and final winning scholarship essay.
It is impossible to discuss the current climate of the judicial system and the eroding rights of immigrants, people of color, women, and the LGBTQ community without discussing the Trump administration and its policies. Donald Trump's presidential election in 2016 was partly due to the overwhelming support of white evangelical Christians. The Pew Research Center puts the number at 81%. This group has remained his strongest base, and he has fulfilled his campaign promises to them, from attempting to limit or outright ban abortion, to blocking transgender people from serving in the military, to drastically reducing immigration. The symbiotic relationship between evangelicals and Trump has leaders of the National Association of Evangelicals boasting about their unprecedented access to the president, and Jerry Falwell Jr. calling him their dream president. There is no doubt that this close relationship has affected recent policy changes. To reverse these efforts and lead the U.S. back to the ideals of human dignity, compassion, and equality for all people, we need to identify religious bias, disseminate accurate information, educate the public, and ensure representation in our leaders. The first step to understanding how religion is creeping into our governmental policies is identifying it. In today's age of labeling things fake that are not favorable to one's own opinion, the role of nonpartisan watchdogs is critical. Americans United for Separation of Church and State, the AU, and the American Civil Liberties Union, the ACLU, are two such groups who fight to defend constitutional rights. Since Trump was elected, the ACLU alone has brought hundreds of legal actions against his administration and other government agencies, including fighting for the rights of DACA recipients, challenging the Muslim ban, supporting the rights of sanctuary cities, blocking the transgender military ban, blocking the bathroom bill, preventing new restrictions on abortion rights, and fighting to prevent employers from excluding birth control under their health plans. The ACLU and AU have millions of members between them and thus have the resources necessary to find and respond to prejudicial Christian morality masquerading as prudent public policy. After identifying religious influence, the next step is to disseminate accurate and fact-based information to the public. The majority of Americans used to get their news from shared sources such as regional newspapers and network news. However, in the digital age, the number of sources has skyrocketed, and more people get their news from sources that speak to their already held opinions. An eye-opening chart published by Vanessa Otero shows the most popular news sources, what types of reporting they conduct, and their degree of partisanship and bias. According to her data, the most conservative biased sources are InfoWars and Breitbart. These outlets are labeled as containing inaccurate and fabricated information and are included in a group of sources noted as being nonsense damaging to public discourse. To combat false and misleading information about government and politics, it is important to get real news and analysis from truthful and non-skewed sources. Another tool to ensure secular public policy is to have a strong public education system. One of the stated goals of the Trump administration is to provide vouchers for religious education. Studies show the detrimental effects such a system has on public education by taking tax dollars from public classrooms, creating unequal standards, and leaving behind students with disabilities or those who need extra help, such as English language learners. By its nature, religious training and education do not emphasize critical thinking skills or science-based learning. In many fundamentalist Christian schools, the opposite is true, and widely recognized theories such as the Big Bang and evolution are either ignored or said to be false. According to the Scientific American, white evangelicals are more likely to say humans have always existed in their present form, a theory known as creationism, than other Christians, Catholics, or non-religiously affiliated adults. It is plausible that children educated in religious schools are less likely to apply reason and critical thinking to public policy and will look to their religious leaders for guidance. Rather than spend our collective money to support religious schools, we should strengthen public education programs that emphasize critical thinking, which leads to increased political and media literacy. Finally, we can help remove religious influence from public policies by ensuring representation in our leaders. It is imperative that various perspectives and experiences shape the policies that affect us all, from local school boards and city councils to state and federal legislatures and wide-ranging judicial positions. One of the most striking statistics of the Trump administration is the lack of racial diversity in his cabinet members. According to Univision, when he took office, Trump's cabinet was 86.4% white, compared to the general population of 61.5% white. Since then, his cabinet has become even more white and male. The statistics for the judiciary are just as homogenous. Newsweek reports that 85% of Trump nominees are white and 76% are men. And the 2 Supreme Court justices he nominated and confirmed are both white males. Judges directly impact what cases are heard and how they are adjudicated, so a lack of diversity of race and gender, much less intersectional representation, is appalling. A concentrated effort to correct the situation is paramount to any future hope of non-biased policies that include all citizens, regardless of race, ethnicity, gender, or religious or non-religious affiliation. Many of the policies enacted or proposed by the Trump administration are in direct opposition to non-religious or equality-minded people. Supporting organizations that bring discriminatory practices to light, such as the AU and the ACLU, and engaging with fair and truthful news sources that inform the citizenry is something we can all do. On top of this, we can vote. Voting for leaders from different backgrounds and experiences, and those that are committed to keeping personal religious beliefs out of public policy, will protect our education system, our judicial system, our healthcare system, and all other areas that make up our shared lives as Americans. Thank you.
Does anyone have any questions for Evan?
Well, she's in a sense here, Evan, you're preaching to the choir, so it's difficult to know. We agree with everything you are saying, but do you see any positive movement toward the kind of support of diversity that you're asking for right now in the current climate?
Of course. And these are conversations I have a lot with my mom about the difference between our generations. So she's Gen X. My Gen Z and millennials are so politically motivated and active, and especially right now, so many people in my life are fully involved in protests every single night, or have been working to, my best friend has been working to combat climate change for the past 4 years. He's one of the ones that sued the government. I just see a lot of people around me who, no matter their education level or background, they all seem to easily unite over political discussions and activism. It's really exciting.
So there's room for optimism.
Yes.
Thank you, Evan. Excellent job, and good luck in school.
Thank you.
Joyce, I'll turn it over to you for the introduction of our speaker.
All right. Our speaker today is Dr. Melinda Hutson, the curator of the Cascadia Meteorite Laboratory at Portland State University. Dr. Hutson followed a circuitous route to her final career choice, starting as an art major who hated her beginning drawing class. So she took an aptitude test, which definitely steered her towards science. But what kind of science? Sampling classes in chemistry, physics, and something called non-majors geology, Melinda closed in on geophysics and got a NASA undergraduate internship. She became fascinated with impact cratering, which naturally led to the geochemistry of meteorites. Chemistry had been the least favorite of her original science sampling. In fact, you could definitely say she hated it. But as she continued working with meteorites and solar nebula while pursuing her PhD at the University of Arizona, her advisor recommended she take a physical chemistry course. What a surprise to find that she had already learned everything in the textbook. Turns out that you can't take classes in theoretical petrology, isotope geology, planetary atmospheres, planetary interiors, etc., without learning chemistry. Ms. Hutson is married to the Cascadia Lab's director, and together they have been doing research on meteorites since 1983. we welcome Dr. Melinda Hutson.
The PowerPoint was originally created for our lab member, Dick Pugh. So you'll see his name in here a lot. He passed away in early June. He was in fact originally scheduled to give this talk. So I'm giving it instead. So I call it Willamette Meteorite and Other Space Invaders. So the first thing is I'm a meteoriticist, which is a mouthful. I'm not a meteorologist, which is what people seem to call me. Meteorologists study the weather. I don't. I couldn't tell you one type of cloud from another or whether it's going to get warm or cool. I do care, I just don't know anything about it. Meteoriticists study rocks from space, and this is what I do. And that involves impacts from out of space. And the question is, how does a meteorologist relate to a meteoriticist? And the answer is, we all come from the same root Greek word, which I can't pronounce, which literally means things high up. So in the 15th century, in English, meteor could refer to any atmospheric phenomena, such as lightning, rain, fireballs, whatever. So that leads you to the split between people who study the weather and people who study things that fall out of the sky after being bright fireballs. So in around 1590, the English word for meteor began to take on a more specific term, meaning, an incoming glowing light that you see in the sky. So before I get on to the Willamette, I wanted to cover a little bit of basic background with some vocabulary terms. Asteroid is a big rock in space. It's originally anything that you could see with a telescope, but telescopes kept getting better, and so the things you could see kept getting smaller. So the American Meteor Society now defines it as anything that's larger than about 6 miles across. NASA will occasionally include objects that are much smaller when they talk about asteroids. And most of the asteroids are in the main asteroid belt between the orbits of Mars and Jupiter. A small number are what we call near-Earth asteroids, and they're in elliptical orbits that bring them from the asteroid belt towards Earth. And if they happen to be in the same spot as the Earth, they can enter the Earth's atmosphere. A meteoroid is a little rock in space. It's smaller than an asteroid and larger than a molecule, which is a squishy definition. Most meteoroids would be dust. Up to 10 meters would be about 30 feet or so, a little over 30 feet. A meteor is something that is passing through the Earth's atmosphere and emits light. Typically, this is at most a few seconds. We have meteor showers every year. Those are where comet particles that have been left behind by a comet as it passed through the sun enter the Earth's atmosphere. So you get a lot of little pea-sized or sand-sized particles. Where it's a bigger chunk of rock, a piece of an asteroid or the moon or Mars coming in, we call it a fireball or a bolide. Technically, the American Meteor Society lists those as different things. In reality, those two terms are used almost interchangeably by most of the meteorite community. The technical definition for a fireball is it's brighter than Venus, and a bolide would be a large one that explodes in the atmosphere, such as the one that went over Siberia and broke up into pieces, and the shock wave from the breaking broke glass windows so that a whole bunch of people were injured by glass breaking. Meteors enter the Earth's atmosphere at speeds ranging from 25,000 miles per hour to 160,000 miles per hour. And when they hit a certain thickness of the atmosphere, friction causes them to heat up and they become hot enough to glow with visible light. They become incandescent. And they are typically incandescent in a part of the atmosphere that's between about 50 and 75 miles up. So when you're looking at a fireball that's coming in, it's at least 50 miles away from you. So it's not right in front of you. When you look up and then look down, your eye has an after image. If you've ever looked at a bright light and you see this green image afterwards, and so people will look up and they'll look down and they'll see the after image go between them and say a nearby hill, and they'll say, yeah, I saw the fireball land, really close, and I went out and picked it up. And I'm like, nope, you didn't. If you saw it, it is a long way away. The people who've actually seen meteorites fall, they were not hot and glowy when they fell. It was like somebody threw a fast-moving rock at you. There have been lots of cases of meteorites going through roofs. They haven't set a single building on fire. They have made holes in the roofs and done quite a bit of damage in some of the houses where they landed. So a meteorite is a rock that fell from space. Once it's on the ground and somebody can pick it up, it's a meteorite. And that's what I study. I study rocks from space. And they range from about a gram, which is a very small, little teeny-weeny thing, to the largest meteorite is the 66-ton Hoba in South Africa. So we pick these things up, and they're made up of a variety of materials. There's not one type of meteorite. And so how do you classify a meteorite? Well, one way is to say, what are they made of? And that led to an early separation into rock, which we call stony, metal, which we call iron because it's mostly iron, metal, and something that's in between, which cleverly is called stony iron. Isn't that creative? It turns out that there's lots of different types of irons. There's lots of different types of, there's two main types of stony irons, and there's a bunch of different types of stony. A more fundamental classification from a scientist's perspective is to look at the one group of stonies that we call chondrites, and then everything else. So what's the difference? The chondrites are leftover pieces of material that built the planets, the moons, the solar system, but never underwent any chemical separation. All of the other meteorites, the irons, the stony irons, and some of the stonies, have been substantially molten once. So they've experienced significant chemical separation. And this process is called differentiation. And an example is this cartoon showing you've got bits of metal, bits of rock, bits of sulfide, just together in a small body. That's an undifferentiated chondritic body. If it gets hot enough and starts to melt, the metal will sink to the center to form a core. The lightest rock will float to the surface and make a crust. And in between, you'll have denser rock, which makes the mantle. And if anybody's taken geology, they know that the Earth has a metallic core, a dense rocky mantle, and a combination of oceanic and continental crust, which is the lowest density rock that you're going to have. And that's what we see with our meteorites. So when we look at the stony meteorites that are not chondrites, the differentiated ones, they include things like basalts from asteroids. They do include a small number of them, turned out to be pieces of the moon's surface that got knocked off in impacts and entered the Earth's atmosphere, so we have free samples of the moon. They do include a few free samples of the surface of Mars, which we've been able to confirm by comparing to spacecraft measurements. So most of our samples are from asteroids, but a very small number are from Mars and the moon. So the chondrites are named because they contain these little round beads called chondrules. And I'm not going to spend a lot of time on them, just these are some pictures of mostly cut surfaces. Up in the upper left corner, you'll see one that's a chunk, and you can see the little beads sticking out. It's also a little rusty. And then there's one that's got a lot of metal. You can hardly see the beads. There's ones that's got a bit of sulfide, but almost no metal. That's the one on the lower left. And then the one in the upper right has no metal at all. And yet they're all chondrites. So chemically, for things that would have been solid floating in space when the solar system formed, all of these rocks are identical to the composition of the sun that you can get with telescopes. The difference is for things that aren't solid, such as carbon, oxygen, nitrogen, hydrogen. If you look at the two samples on the right, the one at the top, all of the iron is chemically bound to oxygen. The one on the bottom, most of the iron is not chemically bound to oxygen, and it's in the form of metal. So there's a huge variety of chondrites, and they tell us quite a bit about the formation and the conditions in our early solar system. And that's what I mainly study. That's my area of interest. When we look at the differentiated meteorites, there's dozens, if not, dozens of iron meteorites. You see a picture of a sliced, etched piece of Gibeon in the upper part of the slide. That's a crystal structure that's an intergrowth of two different minerals that are made out of iron and nickel. One is a high nickel mineral, one is a low nickel mineral, but they're both metal. That crisscross pattern that you see is formed by cooling. And to get crystals that large, you have to cool no faster than about 1 degree per million years. So you're only going to get that kind of crystal structure in a core. So these have to be cores of broken up asteroids that had enough size that these things could cool slowly. People who work on earthquake data, the seismic waves that go through the Earth's inner core show that they go through slightly different speeds in different directions, suggesting very large crystal structures similar to this in the Earth's solid core. So these are important meteorites for studying core formation and giving us information about the Earth's core. The one on the lower left is from a mantle of some asteroid somewhere. We're not sure which one because we've never actually been out to visit the asteroid. It's an ultramafic rock, very similar to ultramafic rocks that we get from the mantle of the Earth. The one in the upper right, which has the lovely name of Milbalilli, it's from Australia, and meteorites are named for the locations where they're found. So NWA stands for Northwest Africa, Gibeon comes from Southern Africa, Milbalilli comes from Australia. That, believe it or not, is a basalt. And if you're from Oregon, you're used to seeing these lovely dark basaltic rocks that make up the Columbia Gorge. You may have them in landscaping. If you do slight tweaking to the chemistry for minor elements, things like manganese and chromium and whatnot, a mineral that on the Earth is black, on the asteroid Vesta is actually sort of a medium gray, and a mineral that on the Earth tends to be dark gray is blazingly white. Vesta is unusual. It's one of the lightest colored surfaces that we see on an asteroid, and that's because the basalts are a little bit of a strange chemistry, so they're light colored, but that's basically a basalt. We do have several different types of stony irons. Some are formed by impact. There's one that appears to be possibly a core mantle boundary sample. Those are called pallasites, and they're large grains of gem quality olivine, which is really pretty, floating in metal. And sadly, they're pretty enough that there are people who get these meteorites and basically melt out all the metal, remove all the metal, and then use the olivines for jewelry. which is fine if you're not a scientist. If you're a collector, that's great. I sort of wince when I see those. Okay, so how many of each of these do we get at the Earth's surfaces? Well, the best representation of what's hitting the Earth is going to be what we see fall from the sky. And we have about 12 to 14 easily recovered meteorites fall from the sky every year. And almost all of them are chondrites. There's a few that aren't, but almost all of them are chondrites. So what that tells us is that most of the stuff that is at least in near-Earth orbits is chondritic. And whether or not most of the asteroid belt is chondritic, we're not sure, but that's what's falling from the sky, so that's what's in near-Earth orbits. Stony irons are extremely uncommon, and irons are, only about 4 to 5%. And yet most of what people find, not most, but a lot of what people find when they go out looking for a meteorite is an iron meteorite. And that's because it sticks out like a sore thumb. If you go out and you kick a rock, it's a rock. A dark rock in Oregon, you're not going to really pay much attention to. If you kick a similar sized chunk of metal, you're going to hurt your foot and you'll notice it. And then if you try putting a magnet on it, you'll go, wow, this thing is a big chunk of metal. I wonder where it came from. And so people find irons and bring them in a lot. Rocks are harder to find. There's a story of one in Northern California where the guy was walking through a lava field, sat down to have a smoke, and decided to empty his pipe by tapping it on the rock he was sitting on, and it went ting ting because it was a big iron meteorite. So we find a lot of irons, but they're not as common. Basically, it's chondrites that are falling from the sky. Oregon is a lousy place to find meteorites because they're all going to look like dark rocks for the most part. There have only been 6 confirmed and officially classified meteorites. Our lab actually classified 2 of those 6, and lab member Dick Pugh was involved in the classification of the Salem meteorite, which predates our lab. So if we're looking at them, we have an iron, Sam's Valley. We have an iron, which is the Willamette. We have an iron, which is Klamath Falls. We have an iron, which is Fitzwater Pass. You see a pattern here. 4 of our 6 are irons. We have a chondrite, which is the Salem, and we have a chondrite, which is Morrow County. So Sam's Valley came up in a dredge bucket. People were trying to look for gold. Klamath Falls was in a road cut sticking out. Somebody went over, there was a big rock in the way, and it's like, oh, it's a metal. The Willamette we're going to talk about. It was hard to miss. I don't remember the story of Fitzwater Pass. I know the guy was out with a metal detector looking for it. And I should know the story better than I do because I classified it, but I don't. The Salem actually landed on a guy's roof. In 1981, a sheriff in Salem was sitting at his house. He'd gotten off work and he was talking to somebody in a patrol car out front, and he heard a bunch of pebbles hit his house and he thought a kid was throwing them at him. And the next morning he went out and found a piece in his driveway, and then he found, his house had a damaged shingle. It was not a big hole, it was a little damaged shingle. He found a couple pieces in his gutter. He found one on the street. Went to coffee, this being Oregon, he went out for coffee, realized he could piece together most of a single stone, decided to go back looking for them, and passed a street sweeper on his way home. Never found any other pieces. And Dick worked with some people at a couple of other universities to get this one classified back in the 1980s. Morrow County is a nice, good-sized piece. It was found by a guy who was lost in the back roads of Morrow County, which is why it doesn't have a more detailed name, because he wasn't quite sure where he was, just that he was in this particular area, and it was definitely inside Morrow County. And the guy was a rock hound, and I wouldn't stop and look for rocks while I was lost, but he did. And he picked up a bunch of interesting rocks from, the side of the road, took them home, left them in his garden for a while, and ultimately realized one of them was a chondrite. And before that was found, before it was recognized in 2010, our lab member Dick Pugh said, nobody is ever going to find a stony meteorite in Oregon unless it hits their house like the Salem did. Well, he was proven wrong. So this one was found by a guy lost in rural Oregon. Okay. So of the 6 Oregon meteorites, the Willamette Meteorite is probably the most famous, and it is the most controversial. It is the largest meteorite ever found in the United States, and it's the 6th largest in the world. It's in the Museum of Natural History in New York City. So it weighs 15.5 tons. It's about 10 feet long by 7 feet wide by 4 feet high. And it was found by 2 men, Ellis Hughes and Bill Dale, in 1902 in the town of Willamette. Willamette is now West Lynn, Oregon. And you'll see that these are a lot of pictures from the Dick Pugh collection. Dick was very passionate about the Willamette. And so he asked me to use a whole bunch of his pictures, and so we will. I probably won't tell you as many stories as he would have because he knew every one of these images intimately. And I just have the text that's on the slide, which he narrated to me when I made the PowerPoint. So this is Bill Dale and not Ellis Hughes. Ellis Hughes, surprisingly, doesn't seem to have very much in the way of photos. His stepson and nephew, Edward, seems to be in most of the pictures, but they found the United States' largest iron meteorite, ironically, on land belonging to the Oregon Iron and Steel Company. That is ironic. And it was 3/4 of a mile away from Ellis Hughes' property. They tried to buy the land that the meteorite had been found on, and Oregon Iron and Steel refused to sell. They didn't know why these people wanted to buy the land because they weren't told, but they didn't sell. So Hughes and Dale stole it. What they did was they put it on a homemade cart. They flipped it over. This is the side that had been up. They built a nice homemade cart, and then they winched it down the hill from the find location to a valley and then a little bit up a hill before they gave up. This photo is probably about 600 feet from the starting position. People kept posing for pictures the whole time. And as I said, this is from Dick's collection, and he's identified most of the people in these old images. It took 3 months to move the meteorite the 3/4 of the mile to get it off of the Oregon and Iron and Steel property and onto clearly Ellis Hughes property, because they didn't move that far. The greatest distance it moved in any one day was 150 feet. This was a very slow process of winching this thing. One of the few pictures of Ellis Hughes is this picture. He's on the left, posing very frontiersmanly-like. I'm dominating my meteorite, about halfway to his property. Interestingly, you can see all the cut timber behind. The place is a mess. Obviously, people were logging. When they got the meteorite to Ellis Hughes' property, they rolled it off the cart, and it wound up sort of sideways. So the point, which had been buried in the ground, was sitting on the ground. The flat surface, which had been the top, was now at an angle. This is when the meteorite became widely known because Ward of Ward Scientific came out representing the Museum of Natural History, took some samples, took pictures, and went back and worked on a publication, which is one of the few publications about the Willamette Meteorite. And these are some of the pictures from the 1904 publication. The meteorite was placed in a shack and surrounded by paper so that people could be charged 10 cents to view it. Because, of course, what's the point of having the US's largest meteorite if you're not going to make money off of it? The holes are where iron weathered out over thousands of years. So it basically turned to rust and weathered out. I'm probably going to say this later, but Dick Pugh located the find location, I believe in the 1980s, and picked up samples of the rust. There was still a slight depression where this had been dug out, and there was a ton of rust there. Some of the rust have pieces of gold. There's microscopic, submicroscopic pieces of gold all throughout an iron meteorite. It's usually in the parts per million or parts per billion. And apparently in these basins, you'd catch leaves and centipedes and millipedes, and you got a natural gold bleaching operation going, and it actually concentrated the gold in the rust as it rusted out. There are squared off tops where people came in and sawed off or chiseled off pieces of metal. Metal doesn't break, it's not brittle, so it's a pain to get a piece off, and yet apparently people did. One of the favorite things to do was stick children in all of the depressions so that you could get pictures of the kids sort of sleeping. I'm sure that's very uncomfortable. In amongst the metal, they had little spikes in their back. In 1905, Oregon Iron and Steel realized that these people had stolen an iron meteorite and they wanted it back. And by the way, they were making money on it. So they offered Ellis Hughes money, I don't know how much, for his trouble, and Hughes refused. He went to trial and lost. This is one of many court cases that has established that, at least in the United States, the owner of a meteorite is the person who owns the property on which the meteorite was found. So if you're renting the property, it comes through the roof and it hits you, you don't own it, your landlord does. Oregon Iron and Steel brought up 6 draft horses, 6 workmen, including Edward Hughes, who'd helped move it over to the Hughes property in the first place, and started moving the meteorite toward the Willamette River. This shows how they moved it with a log sledge and rollers drawn by horses and winched. So you can see the rollers. They got about 1 mile, and Ellis Hughes appealed to the Oregon Supreme Court. And this again is Bill Dale and one of Ellis Hughes' sons. So this got stopped on Blankenship Road in front of the Johnson Farm for months in 1905, awaiting the Oregon Supreme Court. It was now free to go and get your picture taken with the meteorite, and a lot of people did. In fact, so many people went in that they started taking samples off, and Mr. Johnson was deputized to protect the meteorite. And he and 3 of his daughters are in the lower picture. The upper picture has some unknown woman who was happily posing for the picture. These are some of the pieces that were removed while it was sitting on Blankenship Road. Dick Pugh liked to go around and find out where all of the pieces were. He has notebooks with stories for all of these pieces. One of these had been stamped with the words Willamette Meteorite 1903 on it. That particular piece was donated to our lab, so I have that one particular piece at the Cascadia Meteorite Lab. I do not have the other pieces. They're still in somebody's private collection. On July 17th, 1905, a judge awarded the Willamette Meteorite to Oregon Iron and Steel, once again confirming that the property owner owns it. This image, which is courtesy of the Canby Museum, shows the meteorite being winched along prairie towards the Willamette River, northwest of the town of West Lynn. Dick was very excited that they were using a Spanish windlass. I'm probably less excited because I have no idea what the significance of using a Spanish windlass is, but that's what they used to move it. Probably using 100 feet of hand-wound cable, all of which belonged to Ellis Hughes, so I assume he was getting paid for loaning them the windlass and the cable. and that his son and nephew Edward was getting paid to help do this. So they made some money off of it, besides the 10 cents a pop they got briefly while they had it on their property. Using a windlass was a way of moving things in Oregon at that time. They're moving a house in Oregon using a windlass in July 1905 in the bottom right picture. That's from the Oregon Historical Society, and that's being moved in southwest Portland. So apparently that's how you moved heavy things. The steamboat Modoc was used to move the meteorite to downtown Portland proper from what was West Lynn for the Lewis and Clark exposition, which was held in the late summer, I believe, of 1905. And this is a picture of the steamboat on the Willamette River taken in 1907. And that's a fairly heavy, big chunk of metal. And that looks like a fairly flimsy boat to me, but apparently it was sturdy enough to take the big chunk of metal. This is the picture of the Willamette Meteorite arriving in downtown Portland and being moved by an 8-horse team to the Lewis and Clark exposition, probably in about August 1905. And I can't see, it looks like it's advertising on the horses. It says transfer company at some number 1st Street. So you have advertising on your horses the same way we have advertising on trucks now. Loan them your horse, loan them your ad. I had never seen advertising on a horse before this. And it's covered with an American flag. All right. So this is the Willamette Meteorite outside the Mineral Pavilion at the Lewis and Clark Exposition in the fall of 1905. Soldiers from the Oregon National Guard provided security and got their pictures taken. The meteorite is still on its original sledge and rollers, so they were still leaving it on the material that had used to move it onto the back from Ellis Hughes' property. At the end of the exposition in 1905, the meteorite was purchased from Oregon Iron and Steel by Mrs. William E. Dodge. I'd like to know what her first name was. It wasn't William, but that's okay. For $26,000, which would have been about $680,000 in 2011 when I made this PowerPoint for Dick. So that's a substantial amount of money. And she donated it to the American Museum of Natural History in New York. And this is a picture of the American Museum around the time the Willamette was donated. It's from 1902, I believe, if I read the fine print. They had to prepare the meteorite for shipping to New York. This is in a railroad yard. I guess they sent it by train. They are preparing to lift it off the sledge, and it was shipped, I assume, by train to New York. The meteorite was weighed after this photo was taken, and they got 31,000 pounds. I have no idea how they weighed it, but that's okay. This is pictures of the Willamette Meteorite arriving in New York. If you look carefully at the left picture, you can see that the rear wheel is sinking into the pavement. So it damaged the pavement moving it. It was that heavy. So those are from the archives from the American Museum. It was apparently Ward was involved because he liked the way it had been in his photographs in his publication. So they set it up in the museum very similar to the way it had been on Ellis Hughes' land, so that you could stick children in the cavities and take pictures of them again. So there's a 1906 image of it being prepared for display, and then a 1919 image of 2 boys from Oregon sitting in the basins. This is on display at the Hayden Planetarium, which was added to the American Museum in 1935. So they had to move it from its original spot to the Hayden. In 1991, school kids from Lake Oswego campaigned to have the Willamette returned from the Natural History Museum to Oregon. They didn't succeed, but they did make it into the funny papers. Uh, I like this cartoon. The original Hayden Planetarium was closed and demolished in 1997. The Willamette Meteorite was put into the new Hayden Planetarium. The planetarium was actually built around, this hall was built around the meteorite. The meteorite wasn't brought in, they built the structure around it, which means they can't get it out without either cutting the meteorite up or demolishing the building. So as of 1997, they're like, we've got this and we're not losing this. So this is a picture of Bill Hughes, Ellis Hughes' grandson, standing next to the meteorite in the Hayden Rose Center for Earth and Space Science. A 28-pound piece of the meteorite was cut off in 1997 to complete a meteorite exchange with a private collector. So you can see in the upper part where the piece was cut off. You can see in the lower picture a little, I've been told that lots of people banged their head on that piece. They were actually very happy to cut that particular piece off because way too many people had hit their head on that piece. It stuck out awkwardly. And then there's the piece on display from the private collector. In his failed lawsuit, Ellis Hughes had argued that the meteorite was a native relic and had two elders from the Clackamas tribe testify that the meteorite was a holy object that was used in tribal rites. This came back to haunt the American Museum of Natural History in 1999 when the Grand Ronde tribe filed a repatriation action against the museum. By this point, of course, the meteorite couldn't be moved easily. It had been built into the structure. So the American Museum wasn't really happy about somebody trying to get it moved back to Oregon. So they filed a federal lawsuit against the Grand Ronde in the year 2000. After a lot of back and forth, the museum and the Grand Ronde Tribal Council came to an agreement, which is being signed here by the chair of the council in 2000, to ensure access to the Confederated Tribes of the Grand Ronde community to the meteorite. There are certain times that they can go and do whatever rituals they want, and they won't try to get the meteorite out of the museum. As part of this, this becomes a sacred object, and they don't want any more pieces cut off of it. However, a piece had already been, let's see, so that was in 2000. However, they did cut the piece off before the 2000 agreement, and the owner planned to auction it off in 2007, which led to a big media uproar because even though it had been cut off before the agreement, they didn't want a piece sold for a large amount of money from a collector. So among the many articles that were published, there were those claiming insensitivity to the Grand Ronde, an editorial which claimed that the Grand Ronde were preparing to sue the owner. The potential bidders for the meteorite dropped out. The Grand Ronde denied the Oregonians' claim that they were going to sue, and the owner, Darrell Pitt, sued the Oregonian and lost. So this has been one of the most sued over meteorites that I've ever heard of in my entire career. In 2006, a 4.5 ounce piece, a little piece, was purchased from Darrell Pitt, the person who owned the 28-pound piece, by the Evergreen Aviation Museum in McMinnville, again with some controversy. And so a little piece, it says Willamette Meteorite to return to Oregon as part of Evergreen Aviation Museum. It's a very small piece of it. It's not the whole meteorite. In 2019, the Evergreen Aviation and Space Museum gave their piece to the Confederated Tribes of the Grand Ronde. So in the quote that they had, it said, "A piece of the sacred meteorite Tomanoos," and I have no idea if that's how it's pronounced, was returned to the Confederated Tribes as a donation by the Evergreen Museum. It's a beautiful piece. you can see the crystal structure between the high and low nickel. You can see large sulfide and graphite inclusions in it. That would be a great piece to study. It's not going to happen. Okay, so the fallout from all of the litigation and bad press, there's actually been very little scientific study on this meteorite. The American Museum of Natural History will not provide samples to researchers. The early work on a few pieces indicates that the meteorite shows at least 2 different iron-nickel structures, which reflect not the initial slow cooling, but very complex shock effects. That's from a study in 1975. These 2 images are from Ward's 1904-5 paper. So that shows you what people are working with. So in 1986, Dick Pugh located the original site of the Willamette Meteorite and demonstrated using mapping techniques that it was on the strand line for the Ice Age Missoula floods. So what happened when you had the Ice Age floods was an ice dam broke and water with big chunks of ice that had rocks embedded in them flowed down and stranded at a particular level around the Willamette Valley. And this meteorite appears to have been a glacial erratic that came in, floated on a very large ice raft in one of these floods. And they talk about, this is the paper that he did. At the time, there was no Cascadia Meteorite Lab, so Dick was in fact part of the science department at Cleveland High School. And he worked with one of the faculty from the geology department at Portland State on this. And these are some pictures that he took of the location where this was found. And so that would be the upper left image. And it's got a lot more upright trees than it did in the earlier pictures because they've grown back. And then the other 3 images show the path downhill that the meteorite was winched. You can still see some traces in the ground of the compression from it. This is a picture of Dick with that little piece of the Willamette that he'd managed to obtain that had the stamping on it that again has been donated to the Cascadia Meteorite Lab. We also have a lot of vials of rust from the site, and we were hoping to determine when the meteorite actually fell to Earth using radiocarbon and beryllium dating, which will give you the time that it is shielded from cosmic rays. But the results were inconclusive. Apparently the weathering messed up the isotopes enough that we weren't able to get a decent date. So this gives us an ending to my presentation. I'd like to do some work on this particular meteorite. It's an interesting meteorite. It's probably not going to happen. There are lots of other interesting meteorites, and I'm hoping that people will find some additional Oregon meteorites, particularly stony ones. There's a lot of people looking. There have been a lot of large fireballs that should have dropped a lot of material in several places on Oregon. So far, none of that material has been found, even though people have been out searching. So right now, the Cascadia Meteorite Lab consists of me, my husband, Alex Ruzicka, and formerly Dick Pugh until this June. So if you have any information or want to talk about possible meteorites, you can go to our website. You can find my email and send me an email. And with that, I believe I have completed the presentation. So are there any questions?
The visuals on that presentation were amazing, and I love the Willamette meteorite story. I did not know that story, so thank you. I guess I'll start with the first question. You talked about the classifying of meteorites, and I want to know a little bit more about that process. How long does it take? What's that like?
For us, it takes quite a while. There are some labs that do nothing but classify meteorites. They have somebody that can prepare their samples in about a day. Once the sample's prepared, they have somebody, a technician, who can do the analysis. They have a piece of equipment that's ready to go. They can get that information in another day, so 2-3 days, a week at most, and boom, they're ready to submit a classification. We don't have all of that. We're a little mom and pop operation on a shoestring budget. So for us, somebody will send us a sample. We have to send it out to a professional thin section preparer to get a glass slide made of it. The fastest we've ever gotten one back is 3 weeks. It's taken 3 months to get some of them back. So that right there is the first delay. Once we get it back, I look at it with an optical microscope. That usually takes me an afternoon. Then I need chemical data where I need to get on a scanning electron microscope, and I have to schedule that. And that usually takes several weeks before I can get on the piece of equipment. I do the analysis. It takes me about a day to process the data. I'm ready to do the write-up. I have to have a lot of information. If I don't have all the information, then I have to go back to the person who gave it to me and say, you didn't give me this piece of information, this piece of information, and this piece of information. And once I get it, it goes to an international committee that officiates, makes the meteorite official, and they vote on it. People who are from one of the big labs, their stuff gets voted on quickly. My stuff, I've had stuff done in 2 or 3 days. I've had stuff sit around waiting for them to deal with it for 4 months. So I tell people it's about a year process for our lab to get something classified.
Thank you.
Thank you very much for bringing to life the story of meteorite, which probably not many people are aware of, and it is a very interesting way you put it up. And I just like to mention that you mentioned it a little bit, namely that meteorites provides a way to study the history over billions of years by studying the cosmic rays which bombard them, their intensity, their energy spectrum, and the various types of isotopes they produce. So this is a real probe into the cosmic history over billions of years, which is, of course, is a big, interesting subject.
If you want to know a little weird thing, a lot of the meteorites that have fallen recently have been L group ordinary chondrites, which means nothing to you, but that's okay. The interesting thing is, if you look at the argon-argon dates, you can find that there was a large degassing event during the Ordovician, several 100 million years ago. And that's been interpreted as a breakup of the asteroid from which we get the L chondrites. That breakup made a lot of small fragments. In Ordovician rocks, in shales, you find a concentration of basically fossil L chondrites that people have been studying. And somebody said, oh, let's think about what would have happened if all of these meteorites came in, what was going on out in space? And they modeled the dust and debris, and it's enough to significantly cut sunlight and probably explain global cooling during the Ordovician, which would have had nothing to do with an impact on the planet. It would have had to do with a whole bunch of dust from the breakup of an asteroid. And this is how an asteroid can cause problems without ever intersecting the Earth. So again, you study the meteorites and there's all these different connections, and you don't expect yourself to go to climate change, but that is often where you go. So people forget that the sciences are all interconnected. They're like, well, this is very esoteric. Why should we, fund meteorite research? Well, guess what? It has connections to other things.
It's just a comment. You said you didn't know the woman's first name who made the donation. I did a quick search, and Mrs. William E. Dodge, who died in 1909, I found her obit. It did not reference her buying the meteorite for New York, but her name was Sarah Headley, Headley. It's in the comments at Dodge.
Thank you. Thank you.
Cool.
I know you don't know the date that the Willamette meteorite landed, but do you have like a period that it had to have been after such and such a date and before such and such a date?
It had to be during the Pleistocene because it landed on ice. It was part of the last ice age floods. So aside from that, no, I don't have a good date.
What are those? And when I'm not familiar with when that started and ended.
The Pleistocene ice ages go from about 10,000 years ago to like 1 million years ago, roughly. So it's somewhere in there. That's not really useful.
That nailed it down.
Yeah,
But it's at least 10,000 years ago. And see, that's more
yes,
than before.
yeah, it's less. It's definitely at least 10,000 years ago for it to be on the ice raft.
I see.
So aside from that, we were hoping to use the rust to get that information because you sometimes can find the date that it basically left space, but didn't find it.
I'll ask something. So I knew Dick Pugh somewhat. In fact, I sort of, it was through me that he asked to speak with the humanists. And so I mean, I understand his great, both, everybody loved him and his ability to teach and his great interest in this topic. He must have had a lot of resources when he passed away. Were those passed on to the meteorology lab, or how did that work?
Well, not the meteorology lab because we don't do weather.
Oh,
The meteorite lab, they're in the process of being transferred. Dick was a bit of a pack rat, and by the time he died, he was verging on hoarder. And so we have his daughter has been packing up boxes, and we go and get a carload of stuff every few weeks.
Wow.
Books, papers, notebooks, samples, and then it takes me, a week or two to get through everything. I haven't begun to get through everything, but just to get through the samples and get them identified. And so I know there's a lot of material in his notebooks that I haven't dug out yet. I know he had planned on writing a book about the Willamette and didn't get to it. He was a very slow writer, and he was a bit of a Renaissance man. He'd worked on a pottery book, so he had China painters of the Pacific Northwest or something like that. So yeah, he had a lot of diverse interests, but the Willamette was a passion for him, and so as I said, he didn't use computers except to give PowerPoint. He learned how to give PowerPoints. So I made up the PowerPoint for him that I gave today. So he was narrating the information. Otherwise, I would have much less information on this because I'm not an expert on the Willamette. And so it's part of his legacy to give the talk. So yes, he'll be missed by a lot of people. He had a nice long life, and sadly, he went very well. It wasn't sad for him. Sadly for us, he went very quickly, so we didn't have time to say goodbye. But I think he went exactly the way he wanted to, with no lingering, no pain, no just boom. One day he was okay, and a few days later he was dead.
Well, you did him a great honor in your presentation today, so thank you.
Thank you.
Joyce?
Here we are. Would you just repeat that term? You are not a meteorologist. You are a, what was that term again?
Meteoriticist. The field is called meteoritics. So the journal is Meteoritics and Planetary Science. That's the main journal that you find meteorite publications in. So then, once you add the I, the hard C becomes an S, so it becomes meteoriticists, which is kind of weird. Yeah.
So you suggested this came through the Missoula floods then, is that correct? And therefore it originated somewhere back?
Probably somewhere in Canada, and came down with the Ice Age floods.
Oh.
Yeah. It probably, landed somewhere on an ice sheet in Canada. The ice sheet emptied out into one of the glacial lakes that were there, like Glacial Lake Missoula, and came down, rafted on a chunk of ice. That's the conclusion that the people who did the work on it, Dick and John Allen.
And that's really an indication of the power of those floods, when it could take that object that far, and then it was so hard to take it just a few 100 feet or whatever, or
yeah,
locally.
There's no impact crater. That's a large enough chunk of metal that it should have made a hole if it had landed in place in West Lynn. And it didn't. So it docked gently right along the strand line.
Okay, Melinda, thank you so much. That was a very informative and engaging presentation. Thank you for today.
All right. Thank you for inviting me.